Good evening and welcome. My name is Tom Baldwin, and I'm the Dean of the College of Natural and Agricultural Sciences here at the University of California, Riverside. I would like to welcome you to the fifth and final in this series of lectures that the college has sponsored this spring semester or quarter. I have not quite yet gotten the quarter terminology in my head. Tonight we're going to hear from Dr. Bahram Mobasher, who is an astrophysicist. He'll be speaking on the subject of Let There Be Light, the first billion years. Now, if you'll recall from our first lecture in this series, we heard about genes and chromosomes, basically talked about the mechanics of how biological evolution works. Tonight's lecture will be talking about something on a rather different scale, the evolution of the universe starting from the Big Bang. Now, Dr. Mobasher is also going to be telling us, I would imagine, about dark matter, dark energy, part of the universe that we can't really observe. We only know about it by what we can infer by observing other parts of the universe that we can in fact see and monitor. Now, after this lecture is over tonight, there will be a reception outside. You may have seen the table set up out there when you came in. I'll have more to say about that in just a moment. In addition to the refreshments, all of the speakers who have participated in this series, save one, Marlene Zuck, will be here, and they would like to have the opportunity to chat with anyone who would like to talk. Okay, now there are several groups I'd like to acknowledge tonight. First is a group that I've mentioned at all of these lectures, and that is the teachers who are in the audience. Once again, I would like to tell you how much we appreciate your efforts on the behalf of the citizens of this state and our children. So the teachers in the audience, would you please stand up and accept our gratitude. Teachers? It's really wonderful. Thank you all very much. Let me also make special mention of Dale Moore, who's the science specialist for Riverside Unified School District. He's been an enormous help in getting information to the teachers. Dale, I saw you come in. You're around here. There he is. Dale, thank you very much. And I also know that at previous lectures, there have been members of the school board who have been in attendance. And are there any members of the school board here tonight? Bless their hearts. Okay. They are otherwise occupied in an award ceremony. Also, I'd like to acknowledge the Science Circle. Fledgling group has just been started up just in the last couple of months. And it's through their generosity that we've been able to sponsor this lecture series. And I'd like to ask the members of the Science Circle to stand up as well. Y'all please stand up. And I really can't say thank you enough, you folks. Now, for those of you who might be interested in joining the Science Circle, we have packets of information and we'd be happy to share that with you at the end of this lecture. We're also grateful, very, very grateful to Gary Lee, who is the founding chair of the Science Circle, his wife Colette and their daughter Lauren, who are supplying the refreshments for tonight's reception. You guys are just over the top. Thank you very much. I'd also like to recognize our two ushers, Ann Jacobs, who just turned in her written qualifying exams today, I'm told, and Brian Gray, who have volunteered to help us with this series from the third lecture on. Thank you both very much. Now, each of you should have been handed, I hope you were, a questionnaire as you came in this evening. And this will be the second time we've had a questionnaire during this series. We read these things very carefully and try to take your advice to the extent that we can. The one place we have not been able to take your advice is to deal with the parking. But that's something I apologize for, but there is absolutely nothing I can do about it. But if you would like to fill that question, if you would please fill out that questionnaire, it will help us with this series going forward. Now, in the fall, we're going to have a series of lectures, probably 2 or 3. It hasn't been decided for sure. But those lectures, again, will be on the topic of evolution. So we're going to try to take a couple of faculty members whose research is really very heavily embedded in evolution and let them drill down and show you how evolutionary thinking plays a critical role in developing a research project. So the lectures we've had this spring have been fairly general lectures in evolution, and the ones in the fall will take a much narrower area and drill down deeper. Then in the spring semester, the topic that I think is getting the most play is to focus on the science that underpins our thinking about global climate change. Some very, very exciting, very interesting science that underpins how it is that we think about this process. I know it's something that's of general interest to a lot of people, and so we'll try to sort of peel back the mystery on how it is that we go about thinking about global climate change. So watch for the announcements for these series. It will be in the press enterprise and emails and so forth and so on. If you would like to be sure to hear about this, if you will share with us your email address, we promise that we won't try to balance the budget by selling the email addresses to anybody. So if you will share with us your email address, we'll make every effort to be sure that you are informed about the lectures, when they're going to happen, and so on. You can send that information to Sarah Clausen, whose email address is on the back of your program. Now, for tonight's lecture, we're going to hear from Professor Bahram Mobasher, who is an internationally renowned biophysicist whose expertise is in the area of observational astronomy. What this means is that Dr. Mobasher spends his time staring at the sky, watching stars. He usually uses some very large, very, very expensive telescopes to do this. He received his Bachelor of Science degree in physics from the Pars College in Iran, his master's and PhD in observational cosmology from the University of Durham in the United Kingdom. Dr. Mobasher joined UCR faculty in 2007 after 7 years working on the Space Telescope Science Institute in Baltimore. There he was a leader in developing the Hubble Telescope Ultra-Deep Field Project, which searched the cosmos for very old galaxies. I believe you'll be seeing some photographs that have been taken from that project. One of them has become indeed very famous, showing some of the oldest galaxies in the universe, some 13 billion years old. Dr. Mobasher has done some very well-known work on how the ratio of dark matter to dark energy has evolved since the Big Bang. He's also famous for finding a very large and very old galaxy, a discovery that completely changed our concept of how stars and galaxies evolve. In other words, you're going to hear from a guy who knows a whole lot about the topic he'll be talking about. Bahram?
Thank you, Don. It's a great pleasure tonight to stand in front of such a distinguished audience to talk about the universe, how it started, and how it's going to end. I was not born in this country, but I've had the privilege to live in this country and use the opportunities it has provided to me to educate myself and others. This I would be forever grateful for. Tonight, I'm going to talk to you about the start of the universe. We start from the beginning. And then how the universe evolved to the state we see it, and how it's going to evolve in future, and many other things. By the end of this lecture, you know how the universe started, how it's going to end, and how it got to the state it is today. What I would expect you to do tonight is, when you leave this room, you leave it either convinced or confused, but not indifferent. What I would like you to do is, when you look at the sky tonight, you have a different view than you had last night. And this is what I hope I would be able to do in this lecture. I was giving this lecture, a lecture last year. And at the end of the lecture, my 7-year-old daughter came to me, said, "Daddy, your lecture was so interesting, I fell asleep." I hope my lecture would not be that interesting tonight. So let's start from where it all started. The universe, the first model for the universe was proposed by ancient Greeks, and Ptolemy proposed a model. Doesn't seem to work. Ptolemy proposed a model which stood for about 1700 years, until Copernicus changed that. In Ptolemy's model, the Earth was put at the center of the universe, and everything else, the sun and the planets, were moving around the Earth. After 1700 years, Copernicus changed that by removing Earth from the center of the universe and putting sun at the center of the universe. This was a courageous act. For 1700 years, people believed the Earth was at the center of the universe. And after all this time, he had the courage to remove that and put the sun at the center of the universe. This, by the way, looked like me when I had hair. After this is about 1700 years it took us to go from this geocentric universe to a universe where the sun was at the center. About 20 years after Copernicus, Galileo was born. And he was the first one to show that Venus was actually moving around the sun. Not only that, but other planets. Galileo was the first to invent the telescope. And this year is 400th year of the anniversary of invention of telescope. He used the telescope to see Jupiter, the moons of the Jupiter. That was the horizon at that time, about 400 years ago. You'll see tonight where our horizon is. After this, progress continued. And according to Newton, if I've seen further, it's by standing on the shoulder of giants. And Newton himself proposed the theory of gravity. With that theory, we landed on the moon and sent space shuttle off. This is the power of science, what we can do. And that all started many years ago. But at the beginning of the 20th century, our view of the universe was very, very different from what it is today. And in fact, it all started the first half of the 20th century. And the reason for this introduction is to just show you how fast we have moved since then. So the beginning of the 20th century, we realized that the universe started from a big bang, about 13.6 billion years ago. What happened before the Big Bang, we don't know. I'm going to touch on it at the end of my talk. How the Big Bang happened, we don't know. What the situation was before that, we don't know. But we know that it happened, and you see my reasons why it happened. After that, the universe started to expand, and it has been expanding ever since. So what we do, we start from the beginning, when the Big Bang started, when the universe started, and then move forward. So we see the second after the Big Bang. So this is where we started, where the Big Bang started. And after that, we have no information what happened immediately after the Big Bang. The numbers I'm going to quote tonight, you have never heard these numbers. Probably you will never hear them. But these are huge numbers in both ways, both small and large. 10 to minus 42nd after the 10 to minus 43 seconds after the Big Bang. That's the time where we have no information from. So from time 0, the time of the Big Bang, to 10 to minus 43 seconds after the Big Bang, we have no information. We have no physics. We need a new physics to study that. So this is unknown region. Then what was at that point was nothing but light, was the energy, the light, and the force. And the forces of nature, there are 4. There are 4 forces. The gravity, which holds us on the Earth, which holds the planets. It's electromagnetism, which is much stronger than gravity, and depends on the electric charge and not the mass of the particle. And there are strong and weak forces, which operate over extremely short distances. The strong force keeps protons and neutrons inside the nucleus of atom, and weak interaction is responsible for nuclear reaction. So these forces were all one force. There was a super force right at the beginning. And this is before 10 to minus 43 seconds. Right at that moment, 10 to minus 43 seconds, the gravity separated itself from the other 3 forces and went its own way. At that point, the temperature of the universe was 10 to 32 degrees Celsius. As the universe expands, it cools down. So the universe is expanding. It was incredibly hot, 10 to 32 degrees Kelvin. It cools down. As it cools down, it loses energy, and other forces start to go their own way. So at about 10 to minus 38 seconds after the Big Bang, the other force, the strong force, separated from the other forces. The temperature was 10 to 29 at that time. And at 10 to minus 10 seconds after the Big Bang, the other 2 forces, weak force and electromagnetic force, separated. And these are the 4 forces we have. Since 10 to minus 10 seconds after the Big Bang, we have 4 forces, and they have stayed ever since. So these are the forces we see. And this was the history of the universe in, I cannot say fraction of a second, is much less than fraction of a second. So at that moment, 10 to minus 10 seconds, the grand unification time ended. And here we have all the forces in nature which we see today. And this is the beginning at the bottom and going up with time, what happens. So I'm going to move up from beginning to where we are now. After this, as the universe expands, it cools down. The temperature of the universe goes down. As the temperature goes down, the elementary particles which are produced in the very early universe, those elementary particles get together. The most fundamental particles are the quarks. And here we have at the 1,000th of a second after the Big Bang, the beginning of the universe, we have the quarks getting together. 3 quarks forms a proton. So an atom consists of a nucleus which contains 3 quarks. A nucleus which contains proton and neutron. And each of these proton and neutrons contain quarks. So 3 quarks forms a proton and neutron. And these quarks got together and produced these elementary particles, protons and neutrons, right at that moment, 1/100th of a second after the Big Bang. Before that, it was difficult, because as protons and neutrons were formed, the intensity of radiation was so high that disintegrated that. So that produced a delay in creating all these particles. And when it was formed, the proton and neutron got together and produced the nuclei of atoms, the simplest atom being hydrogen. So hydrogen atom was produced by combining proton and neutron. And this is the beginning of this, the formation of elements. From 1,000th of a second to 3 minutes after the Big Bang, the elements, the nuclei, were produced and were destroyed by heat and radiation, which was very intensive at the beginning of the universe. So right at the 3 minutes after the Big Bang, what happened was that the universe still is expanding. The temperature and the energy became so low that these could form. So we could form stable nucleus. So the nucleus could form and not disintegrate by radiation, by intense radiation. At that point, 3 minutes after the Big Bang, we formed nucleus. The first one was hydrogen, the simplest of the nuclei, and then followed by helium. 75% of the element, of the matter at that time, went into hydrogen, and 25% to helium. This is the hydrogen and helium we have today. The hydrogen we have in our water, we drink, and the helium we have in the atmosphere are leftovers from the Big Bang, from 3 minutes after the beginning of the universe. So when you drink water, remember that's the Big Bang, remnant of the Big Bang you're drinking. That's the hydrogen which is left over. Hydrogen cannot be produced through stellar evolution throughout the age of the universe. This is one of the reasons that we believe in Big Bang, because this directly agrees with what we believe with Big Bang models and with observations. 75% of the matter is hydrogen, 25% helium. And these hydrogen and helium get together, fuse, and produce heavier elements. And this is why and how we have heavier elements. From 3 minutes to 380,000 years after the Big Bang, what happened was that we have nucleus now. We have nuclei of hydrogen and helium. But what happens to form atoms, we need electrons. We need electrons to get around this nucleus and produce the atoms. But again, as soon as the electron comes and combine with nuclei and produce the atom, it gets disintegrated because of the heat, radiation, and energy. As soon as the energy became less than the potential energy, the binding energy of electron, the atom was formed. And that was about 380,000 years after the Big Bang. The first hydrogen atom was formed. The rest is, and the temperature there was about 3,000 degrees Kelvin. The rest is history. So what happens is that these atoms combine through stellar evolution, produce heavier elements. And this goes through 13 billion years. And it has gone through 13 billion years, the age of the universe. What we had at 380,000 years after the Big Bang was the atoms in the universe, lots of radiation still, but with less energy. And these atoms and radiation at that point start to decouple, go their own way. They do not interact with each other. And today, we see leftover from that radiation. That's cosmic microwave background radiation. And this is the radiation which is observed today. And this is the second evidence for the Big Bang, why we believe on Big Bang. You see this? That's distribution of that radiation. And you cannot see the creation any closer than this. What you see here, the dark points, are seeds of galaxy formation. This shows us distribution of matter at 300,000 years after the Big Bang, after the beginning of the universe. And this is how the matter was distributed at that time. We see the remnants of that today, and I'll come to discuss that later. So what we have, this shows the change in the temperature from the Big Bang, 10 to minus 45 seconds after the Big Bang. The temperature goes down continuously until now, 10 to 15 seconds after the Big Bang now. So the temperature, because of the expansion of the universe, goes down and continuously goes down. This is the end of the beginning. So what we now have is stars and galaxies form through all these material we have. And the heavier elements start to form throughout stellar evolution, throughout the age of the universe. Before going any further, let me give you some definitions, because it's important to see what we're talking about. So what are stars? Stars are basically clouds of gas and dust. Our sun is a star. Remember, our sun is a star. There are billions of stars in our galaxy, and stars evolve as their luminosity changes, and they eventually die in the form of black holes or supernovas, depending on their mass. Stars look like something like this. This is a gas cloud with stars around it, and this is a star cluster. The galaxies are a collection of 100,000 million stars. So there are 100,000 million stars on average in any galaxy. Galaxies are the main components, constituents of the universe, and they are moving away from each other. Our Milky Way is a galaxy, and that contains 100,000 million stars. Our sun is only one average star in our Milky Way galaxy. Galaxies evolve with cosmic time. This is an image of a galaxy. That's 9 million light years away. And this is another galaxy. This is what a galaxy looks like. And there are hundreds of thousands of millions of these in the universe. Now, all these reside in the universe. The universe started from the Big Bang as we saw it. It's expanding now. And the universe, all the galaxies in the universe are moving away from each other. If you blow a balloon and mark on the surface of the balloon, the points start to move away from each other. This is how this resembles the expansion of the universe. All the galaxies move away from each other. This does not mean we are in a certain place in the galaxy. If you go to any other galaxy, you see the universe expanding. And the expansion started from the Big Bang, from the beginning. This was first discovered by Edwin Hubble in 1929. Hubble was not too far from here in Mount Wilson Observatory. Hubble was born in Missouri and was educated in University of Chicago, and then went as one of the first Rhodes Scholars, went to Oxford and did law. And this is the diagram, the first diagram which he produced showing the expansion of the universe. This, the horizontal axis, is the distance, the vertical axis, the velocity. Speed and distance with galaxies are correlated linearly, as you can see here. The speed is v, and the distance is r, and h is the Hubble constant. These are correlated linearly, and this is the Hubble law. And this was the beginning of modern cosmology. Indeed, he studied law, and you need a lawyer to convince you that there is a relation here on this diagram. Now, the cosmic background radiation I mentioned is one of the leftovers from the time of the Big Bang. So let me give you a thought example. If we leave our solar system, we go to our galaxy. And if we leave our galaxy, we go to the universe, intergalactic medium. If you measure the temperature in the intergalactic medium, what temperature you get? You get something like 2.7 degrees Kelvin, minus 270 degrees centigrade. That's the temperature of the universe. So the temperature of the universe is not zero. Minus is very, very cold, 270 degrees centigrade. And that is the temperature which is left over from the Big Bang. Remember, it was hot Big Bang. It was old radiation. This is the leftover radiation of the Big Bang. Wherever you measure it the same. You measure it the same intensity, showing that its source is cosmological. So that is the temperature of the universe. And the points you see here, the red points, are points where there is matter, more matter there. And this shows the structure at the time where this is decoupled from radiation, about 300,000 years after the Big Bang. So this directly gives you information soon after the Big Bang. Now, having said all this, let's see where we are in the universe. We live on a small planet called the Earth. The Earth is a planet in the solar system moving around a star called the Sun. The Sun is one of the 100,000 million stars in our galaxy. And the solar system is right at the edge of the galaxy called Milky Way. So here is where the solar system is. And the Milky Way is a part of the local group of galaxies, which itself is a part of the local supercluster. There are 100,000 million galaxies like the Milky Way in the universe. So let's put it this way. The Sun, there are 100,000 million suns in our galaxy, and 100,000 million galaxies like our galaxy in the universe. And in each of them, there is about 100,000 million stars like the Sun. So this is the number we are dealing with. The distance between us, our galaxy, and the local supercluster, the common cluster, is about 100. It's 60 million. Yeah, it's 60 million light years, meaning that light has taken 60 million years to reach us from that local supercluster. And that's local. That's the closest superclusters we have. To do all these, we need to measure. And according to Galileo, measure what is measurable and make measurable what is not so. The scientists do their estimates and calculations by measurements and observation. And one way for us astronomers to do these measurements is by telescopes. This is the Hubble Space Telescope in the orbit, about 350 miles above the Earth. And this is one of the pictures which is taken by the Hubble. Every one of these small dots you see here is a galaxy, which contains 100,000 million stars. Every one of those dots is a galaxy which is about millions and millions of light years away from us. And we see it today. The bigger ones are closer galaxies. Colors mean something. The redder galaxies are older or are at higher distances. The bluer galaxies are younger. So that's how we use colors of galaxies to see to know about the physics of these galaxies. All these galaxies are moving away from each other. And the speed with which they are moving is about from 10,000 kilometers per second to 100,000 kilometers per second. So that's the scale we talk about. And these are some images which were taken by the Hubble. And you see some details in these. I'll repeat, every one of these single dots you see here is a galaxy, is a huge galaxy containing hundreds of thousands of millions of stars. And the reason they look so small is simply because they are too far away. These galaxies look bigger, so they are closer. It's not easy to take these pictures, and you see the details you get from Hubble. You see details in this galaxy or in any other galaxy you could study. So these are the pictures we get, and it's not easy to get that. One of the biggest projects which I've had the honor to be involved with was the Cosmos project. And you see here, the Cosmos area compared with the size of the moon. The principal investigator of Cosmos is sitting here, is my close friend. And we started this project with a few people, and it grew to a large international project now. It's 9 times the size of the moon. And this has taken a huge amount of effort and time to get to that stage it is. 9 times the size of the moon is not large area. If you look at the moon in the sky, it's not large area. So it's so difficult to do that for such a small area. So you could imagine how difficult it is to get such images. So we talked about the formation of heavy elements in the universe. And now these heavy elements, carbon, nitrogen, oxygen, are the basics of life. So what we want to see is how these help to get us where we are now. The elements were formed in stars. So the heavy elements were cooked in the stars through stellar evolution. And then when a star dies, it ends up with supernova, which is a huge explosion, as you can see here. It's one of the most, it's very, very big explosion. It gets as bright as a big galaxy. And the supernova, when they explode, they disperse the elements, heavy elements in space. So the heavy elements are dispersed in the intergalactic medium, interstellar medium, by supernova explosion. And they end up in some of the planets in which life conditions are suitable. And this is how life starts. So the life basically comes by explosion of supernovae and dispersion of material in the interstellar medium, eventually landing on some planets. You see here, it's the Time magazine. The other news that day, many years ago, was the spy case in Israel. And supernova explosion was more important than spy case, because it happens rarely. Well, less often than the other one. So what we do now is to search, and many of my colleagues are working on this, for the planets. And there are to date, there are about over 100 planets are found which look like the Earth, with the possibility and potential to develop life. And these are some of the, we have been looking for these planets with different missions. NASA's Kepler it's been launched, and this is looking for a planet, and in future we will be looking to see if there are signs of life on these planets. Once supernova explodes, this heavy material land on some of these planets, they could develop life, and then we might be where we are today. So here, to conclude, I put the evolution of the universe from the beginning in 1 year. I scaled it to 1 year. So if the universe started the 1st of January, by February, the Milky Way, our galaxy, was formed. By 3rd September, the Earth was formed. And by 22nd September, early life on Earth was started. Then it goes like that. December 30th, towards the end of the year, the dinosaurs were extincted. And December 31st, that's where everything we know started. 9 p.m. on December 31st, the first living organism started to evolve. And then 11:58 p.m. on December 31st, we have only, well, we're nearly the new year. The modern humans evolved. So you could compare, scale it back, see how small, how short of in the history of the universe we are looking at. 11:58, December 31st, we were just started to evolve. And 25 seconds ago, agriculture, as we know it, started. So it's the tiny history we have compared to what the universe has. I hate to think what would have happened if that year, December, had 30 days. Now, one important issue here is the first galaxies, how we see them and how we understand and study them. We could now see the first galaxies, and this is how we find them. Think about it. By looking at distant regions in the universe, we look back in time. By looking for the most distant galaxies, we look at the beginning of the universe. If you look at the sun, the sunlight takes 8 minutes to get to us here. So when we see the sun as it was 8 minutes ago. Similarly, if we see a galaxy which is 10 million light years away, we see it as it was 10 million years ago, because it has taken light 10 million years to get here. Because speed of light is finite. Therefore, when you look at the sky, essentially you look back in time. Further away you get closer to the beginning of the universe. So if you pick up the most distant galaxies, you could claim to have found the first generation of galaxies formed right after the Big Bang. This is how this is done. This is how we look for the first generation of galaxies. Try to find the most distant objects in the universe. And once we find the most distant objects, depending on the distance, we see how close we are to the beginning of the universe. And here we can see the formation and evolution of galaxies. Here you can see that's the Big Bang, and we are sitting here. When we look back in time, and time goes this way. When we look back in time, time zero, we get closer to the Big Bang. further away we go, we start to get closer to the Big Bang itself. This is one of those galaxies, one of the most distant galaxies. I don't know if you can see it, but it comes up. And you cannot see, again, closer to formation of galaxies than these ones. So this is how you find these galaxies. To find the most distant objects, light has taken 13 billion years to reach us. Therefore, you look back in time 13 billion years ago. So by looking at this galaxy, we see it as it was 13 billion years ago, not as it is today. Some time ago, a few years ago, we started to think about this, that what would the deepest image of the universe be like? If you take the deepest image ever of the universe, what would you see? And here is where the Hubble Ultra Deep Field was born. This is the deepest image ever taken of the universe. And we thought that as long as Hubble is up there and is working, we should use it and do it. And this is how we did it. And the reason for doing it was simply this: to look back in time, as back as you possibly could, to start to pick up and find the first generation of stars and galaxies. This is where Hubble is and where we are. By looking further and further away in the universe, you get to the point where you start to pick up the first generation of galaxies and stars. The observations must be so deep that you get close to the beginning of the universe. And this goes back about nearly 13 billion years. So when the universe was about 600 million years old. At that point, we could start to see that. And today, you see the deepest image of the universe. This is Hubble Ultra Deep Field. That's the deepest image of the universe. And this is going to be the most important hour in your life. You know how the universe started. You know that you see the deepest image of the universe. And you see a lot more. This is the Hubble Ultra Deep Field. So any of these dots, again, I repeat, is a big galaxy. A galaxy which is 10, 12, 13 billion light years away. So when light left these galaxies, the Earth and the solar system was not here. So essentially, we are looking back that much in time. And today, these galaxies may not exist because we are looking back as they were, not as they are now. In studying this, we found a new population of galaxies, a population which is extremely massive and very old and very distant. The question is, an object cannot be both distant, because if it is distant, it's young, by definition. You look back in time. It cannot be massive at that distance, because it hasn't had time to form its mass. And it cannot be old, because it hasn't had time to grow. So what happens? This old galaxy, massive galaxy at large distance. So something must be going wrong. I don't know what's going wrong. The only thing I could think of is we've done something wrong in finding these galaxies, but different tests have shown that we haven't done anything well, or not. We haven't been in serious error. This is one of those galaxies you see here. That red point, you see that. And this was found in Hubble Ultra Deep Field. One of the, and this is really a puzzle. And if this is found to be true someday, it would be a crisis in cosmology. Because we cannot explain how these objects formed so early in the history of the universe and so massive at that time. That's the comment which I like. And this is how we use these and find these new techniques. It's common sense to take a method and try it. If it fails, admit it frankly and try another. But above all, try something. That's what I keep telling to my students. That don't be despondent if you don't find things, if things don't go the way you want it. If you fail, if your technique doesn't work, try another technique. Admit it's wrong. That's something scientists don't normally do. Admit it's wrong, but try another thing. And try. The most important thing is try something. evolution of galaxies. So galaxies were formed. These evolved throughout the age of the universe. Galaxies evolved by merging. Galaxies collide. And our galaxy is the result of mergers of galaxies many, many billions of years ago. And it evolved to get to the present shape. This is a galaxy, two galaxies in the process of merging. It's a very violent process, but it happens very often in the universe. And this is the evolution of the structure in the universe we see, from 500 million light years to 150 million light years to 35 million light years. So this is the most distant and evolves with time as we see it there. This is simulation. This is not real data. But this is how the galaxies evolve. The structure evolves in the universe and gets to the place where it is today. Here you see a picture, the top to bottom. That's from the most nearby to the most distant galaxy. And you see how the structure of galaxies change and how galaxies evolve. To study evolution of galaxies, what we do is just like studying a tree, a plant. So if a tree is 50 years old and you want to see how it evolves to get to that old, there are two ways to do that. One is to plant a tree and look at it for 50 years, see how it evolves. The other way is to find different trees of the same type and look at them of the same type at different times during their lifetime and compare their properties. This is how we study the evolution of galaxies. We find galaxies of the same type at different distances, look back times, and compare their properties. And this tells us how galaxies evolve throughout the age of the universe. Next topic is the content of the universe. What is the universe consist of? And this is mainly dark matter and dark energy. So the matter we see in the universe, it's only 4% of the matter. It's about 96% of the matter in the universe is dark, cannot be seen, cannot be observed. So the matter you see, the stars you see, the galaxies you see, that's only 4% of what you see in the universe. Dark energy is even more complicated. It's about 76% of the content of the universe is dark energy. And here you can see it. So 73% is dark energy, and about 27% is matter in the universe. Out of that 27%, only 4% is the matter we can see. 23% is dark matter. Dark matter could by itself close the universe. The universe we are seeing is expanding. The question is whether this expansion stops at some point and contraction starts, or that continues to expand forever. That dark matter could answer that question once we know what it is. Here you see different shapes. So the universe started from this point and expanded. And at some point, if the mass density of the universe is higher than a critical value, then the universe stops expanding and starts to contract. And that's what we see in a closed universe. If the matter density is smaller than a given value, than a critical value, the universe will expand forever. So this we can now observe and see what the universe, what the future of the universe is. So the future of the universe is dictated by dark matter and dark energy. And dark matter is so much which could close the universe. And here is how we measure it. We have an object there, and the light from the object comes to our eyes. And if we have some matter in between, according to general theory of relativity, that bends the light and distorts the image of that object. From the distortion, we could find the amount of matter in between. And here is how we find the dark matter. Dark matter cannot be seen. So from its dynamic, from its gravity, we should study the existence. And this is how it's seen. And this is a picture of how a lens cluster would look like. All these arcs you see, this is because of the lensing. This is called gravitational lensing. And it's used for estimating dark matter, the amount of dark matter in the universe. And for the first time, we managed to find the dark matter distribution in the universe in our team in Cosmos. And this shows how dark matter is distributed in the universe back in time from 3.5 billion years ago to 6.5 billion years ago. This is how dark matter is distributed. This is not easy. You're basically looking at something which you cannot see. And you just find out how it's distributed. Not only that, how distributed with the age of the universe. Dark energy is more complicated. And here is, this, as you will see in 2 minutes, this could dictate the future of our universe, where we are and where we're going. Basically, it goes like this. You take a given galaxy. You find the distance to that galaxy from dynamics and from law, Hubble law, V equals HR. So you measure the distance to that galaxy. And you also find the real distance to the same galaxy. You have to have one distance for any given galaxy. But what happens, you end up with 2 different distances, with the dynamic distance being always smaller than the real distance. This means that you need a force to shift this. This means that you need a force to shift this to that distance. And this is the force of dark energy. What dark energy causes is the gravity to have a repulsive effect. So galaxies would repel each other. So it would help the expansion of the universe. It would accelerate the expansion of the universe. Everything would move away if dark energy exists. And this is what happens and how it goes. The horizontal axis is the distance. This is the present, and this is the past. So from present to the past. And the vertical axis is the same thing I said, the difference between the 2 distances. The curves you see are different predictions of the models. So the bottom, the yellow curve, is when the universe is in a state of constant deceleration, meaning that if dark matter is affecting the expansion of the universe, decelerating the expansion. And the top dotted line is the constant acceleration, meaning that if dark energy is dominant. If our data points, these are models, if our data points follow any of these lines, the universe is following that. That is what the universe is. Now what I'll do, I put the data point on these lines, and you see which one it follows. If it follows the yellow line, it means the universe is decelerating, meaning that the universe will be closed. The expansion would stop at some point. If it follows the other one, the dotted line, the dashed line, the universe is open and would accelerate and would expand forever. If it lies between the 2, it means the universe went through a phase transition from a decelerating universe to an accelerating universe, or vice versa. I put the data point on now. And these are the data points which, by the way, was not easy to achieve. So it goes basically, it's inconclusive now. And here, it follows a line between the 2 lines, meaning that the universe sometime in the past was decelerating. The slope of that line is similar to that deceleration line. So the universe in the past was decelerating. And sometime, and sometimes it went through a phase transition from deceleration to acceleration. So in the past, because the slope of these data points changed at some point in time, and this is the time when the universe went from a decelerating phase caused by dark matter to an accelerating phase caused by dark energy. And we are now living in that universe, a universe which is accelerating. When did it happen? We could very easily see that when the slope of this line changed. It changed at this point, which is about 4.2 billion years ago. So the universe, about 4.2 billion years ago, went from a decelerating phase to an accelerating phase. The expansion was, the speed of expansion was decreasing before that because of dark matter. But at that point, for some reason, dark energy took over, and the universe started to accelerate. 4 billion years is not a long time ago. It's when the Earth was formed. When the Earth was formed, the universe went through this phase transition. I want to say how, in detail, we could study these things today. And the future of the universe really depends on the competition between dark matter and dark energy. If dark matter dominates, then the universe would be closed. We have gravity, and that closes the universe. If dark energy dominates, we have anti-gravity. The gravity has a repulsive force, and the universe would accelerate and would be open and would expand forever. I mentioned that 76% of the content of the universe is in the form of dark energy, meaning that dark energy dominates, meaning that the universe is open and is going to expand forever, if our data are correct. Based on this scenario, let's see what happens to the future of the universe. But before that, this is a nice comment by Isaac Newton. There is one thing stronger than all the armies of the world. That is an idea whose time has come. So this is a table, and I'm going to run you through this table. It won't take more than 1 minute to see where we go. The universe started from Big Bang, and then the first 3 minutes we went through all this. The elements were produced in the universe. And then about 100,000, 300,000 years after the Big Bang, the atoms were formed. And 1 billion years after the Big Bang, the first galaxies were formed. We could see that today, and we saw it. About 13, 14 billion years after the Big Bang, that's where we are now. And where are we going in future? If dark energy is correct, if our calculations, the scenario, dark energy scenario is correct, this is what's going to happen for the future of the universe. Now I turn the movie the other way around. 1 billion years before the end of the universe. The effect of dark energy increases with time. So it increases, becomes stronger with time. So 1 billion years before the end of the universe, the galaxy clusters would erase, would just disperse. About 60 million years before the end of the universe, the Milky Way, our galaxy, would be destroyed. Dark energy would be so strong that it goes to galactic scale structures and basically disperse them. 3 months before the end of the universe, the solar system would be destroyed, would be unbounded. And 30 minutes before the end of the universe, the Earth would explode. So once the Earth exploded, we know we only have 30 minutes to leave. 10 to minus 19 seconds before the end, the atoms dissociate and the universe ends 35 billion years from when it started. This is all hypothetical, don't worry. That only depends if our model works and everything else works. But in any case, it's 20 billion years away, so who cares? So what's going to happen in future? We have come 100 years since the first manned flight happened, right, brother? And today, in fact, 2 weeks ago, we launched the shuttle as the final visit to the Hubble Space Telescope. It visited the Hubble, and it repaired the Hubble. And Hubble is now a new telescope. Could work for another 5 years, at least for another 5 years, stronger than ever. And we are going to work on it, write proposals, and do great science on it. At the same time, the same week, 2 satellites were launched by Europeans, Herschel and Planck. One to see the origin of the universe, the other one to see new population of galaxies in the universe. They were launched on the same rocket and went to space. We were very worried that 2 very important missions were on the same rocket. And it was a banquet, and I was talking to head of the science department at the European Space Agency. And I told him, I don't know whose silly idea was it to put the 2 on the same rocket. He said it was mine. I left the banquet. And these go to space and go to an orbit very far away from where we are now. The next generation, the successor to the Hubble, is James Webb Space Telescope. It's about 9 times more powerful than the Hubble. And by the middle of next decade, it will be launched in space in an orbit which is called L2, Lagrangian 2 orbit, which is about 1.5 million kilometers from the Earth. That's beyond the moon. So you basically put it there to be away from all the background and the problem. This is so powerful that would have no problem in detecting and seeing the first generation of stars and galaxies. This is why this is designed for, this telescope, the James Webb Space Telescope. 1.5 million kilometers from the Earth. You have other missions, joint dark energy to look for dark energy, and other missions. So the future is bright, as far as we could see. And on the ground, we have 30-meter telescopes. University of California, with Caltech and Canadians, are designing the largest telescope ever, and they're planning to build a 30-meter telescope. That would be one of the biggest telescopes, the biggest telescope we have on the ground. And this is, again, sometime next decade, we're going to have. These all combined, we should be able to know a lot about the universe. The only limit to our realization of tomorrow will be doubt of today. We have to doubt, and doubt, we pose questions. And to answer those questions, we go and do these missions, to find the questions, to find the nature of the truth. So, in the last minute of my talk, I want to think a bit, be a bit philosophical. So, what's the ultimate question? How did it all happen? And who is responsible for all this? The short answer is I don't know. But at least I could think. And the way I think is as follows: that everything in the universe is governed by laws of physics. It's physics which produces chemistry. Physics produces atoms and molecules, and those are bases for chemists. And chemistry leads to biology. Everything, if you trace back, goes to the laws of physics. Therefore, the question I'd like to pose is this: which one came to be first, the universe or the laws of physics? I have been thinking about it for a long time, and I do think about it when I am in rush hour or in traffic or on vacation. I know there is no answer to this, but the question is this: if the laws of physics were created first, before the universe, then the universe must have happened according to the laws of physics. It must have been deterministic. So the laws must have dictated the creation of the universe. In this case, we should know how the universe was created, but we would never know who and how the laws of physics were created. On the other hand, if the universe started first and then the laws of physics in the universe, then the universe must have formed spontaneously, by accident. And somehow in the universe, the laws of physics must have formed. In this case, we would never be able to know how the universe started, but we might one day be able to know how laws of physics started. So this is the fundamental question which I have personally, I have no answer to. I don't know the answer. But the other thing is that why the universe is the way it is. Think about it. If the expansion of the universe is a bit faster than it is today, then structure would not have formed in the universe, meaning galaxies would not have formed. Stars would not have formed, and we would not have been here. If the expansion was a bit slower, then the structure would have formed much earlier. Again, we would have had problems. At the very beginning, I mentioned how the radiation dissociates the atom. If the binding energy of electron in hydrogen was a bit higher or lower than 13.6 electron volts, it would have changed everything. We may not have been here. So everything has come together for us to be here. So everything has happened the way it should happen for us to be here. And this is a comment by Einstein. What really interests me is whether God had any choice in the creation of the world. Finally, why do we do research in basic sciences? We are living in a time, in a particular time in the history of mankind, that we could answer to many questions which have occupied the minds, the greatest minds, for centuries. We've just started to answer many of those questions. Not only we can now answer those questions, we could study them, we could observe them. We could demonstrate how it is. This is the unique position we have, and we should use it. This is why we need to use our position, our unique position in the universe, to study how the universe started, how the universe evolves, and find answers to all these questions. What enriches our children's lives is not the wealth we leave for them, but rather the fascination of finding the unknown, the pleasure of asking questions, and the joy of acquiring knowledge. This is our most valuable heritage we can leave for our children. We know so much about the universe, and yet not much. My friends, I've never been so excited as I am today in doing cosmology. Every week, we find something new. We find the answer to some of the most fundamental questions. Especially last 2 weeks, some of the major missions took place. And within the next few months or years, we could find fundamental answers to many of our questions. At the beginning of my talk, I said I want you to leave this room either convinced or confused. I'm now convinced you are leaving this room confused. But that's good. That means this has had an effect on you, and you have started to spend some time thinking about this vast space. And what we need to know is to acquire more knowledge and more understanding of how this all works. As Plato said, we can easily forgive a child who is afraid of the dark. The real tragedy of life is when men are afraid of the light. Here goes the title of this talk, Let There Be Light. Let there be the light of understanding, the light of knowledge, the light of tolerance. Let's not form an opinion before understanding it, before having reason for it. And once forming an opinion, let's accept other opinions. This is the way the science goes. Many of the material I spoke to tonight were discovered over 5-10 years ago. If I were to give this talk 5 years ago, I would not have been able to talk about any of these materials I spoke tonight. Similarly, if I'm going to give this talk in 5 years from now, with the speed science is progressing, I don't know what I'm going to talk about in 5 years' time. I don't promise I will talk about the dark energy and tell you how the universe started, how dark energy is. I don't promise what dark matter is, and I don't promise to tell you the nature of the first generation of galaxies. But I promise you one thing, I would still have a lot to say. Thank you.
Yes, son. I have a question that bothered me for a long time. And that's at the beginning of the Big Bang, was it pure energy or was it energy plus matter? Because it appears that all matter evolved within for a second.
The Big Bang, the Big Bang started with matter and energy, or right? There was no matter as we know it at the time of the Big Bang. It was all energy and all radiation. And matter was generated later as the universe expands and cools down. Yes, that's right. At the very beginning, yes.
Hi, Professor Mobasher. I have one question. You showed a very old galaxy, a very old and massive galaxy. When was that found?
Testing.
Very old and massive galaxies?
Yes. From Hubble Ultra Deep Field, you showed a very old and massive, like you said, that
That's right.
the galaxy was formed. It's really far away from us.
Yes.
And it is old already.
Yes.
And when was that found?
When was that found?
Yeah.
What year?
Yeah.
You mean last year or?
Yeah.
2005.
In 2005. Do you know anything about like how did that happen? Like
How did it happen?
theory behind it? Do you have any theory behind it, like how that galaxy?
Well, you could develop theories to explain that. Yeah, but if these galaxies are found in great numbers, then theory would be in trouble.
Okay.
Hello. Thanks for your very enlightening talk. So quite a long time ago, I had read about a theory that was the universe expanding, and then at some point it was going to contract and end up with a big crunch. And so my question is, was that a valid idea, and what happened to that theory?
Yeah, that's certainly valid, and we covered it here. If the dark matter dominates the universe, the gravity produced by dark matter could stop the expansion and the universe could collapse. But what we found recently is that there is dark energy, which repels galaxies, makes the universe to accelerate, and that's more dominant than dark matter. So as it is now, the universe is open and it's going to expand forever.
Bahram. Someone else first? Go ahead.
Yes, I was curious what I understood you right. There was a phase transition about 4.2 billion years ago where we went from deceleration, which was kind of ruled by dark matter, to the acceleration with dark energy. That's about the time that life began to evolve on Earth. I'm wondering if
That's the time the Earth was formed, but life started to form later.
Bahram, you're right about being confused. You made the argument that with Hubble early in the 20th century and the discovery of the expanding universe, that's what led to the Big Bang Theory. Now when we discover dark energy and dark matter, why don't we question whether that idea was right?
The expansion of the universe or the Big Bang? I mean, we see the expansion of the universe, so that cannot be wrong. We measure it every day.
That doesn't mean it had to have started at point zero. If we have other things now that are making it go faster and faster, then clearly it's not so simple.
There are valid reasons to believe that started at Big Bang, as time zero. And one of them is the existence of microwave background, which is the leftover radiation from a hot beginning. If you don't have Big Bang, you cannot explain microwave background radiation. The second thing is light element abundance. 75% of the elements is hydrogen, 25% helium. This is exactly what you expect in the Big Bang theory. And the expansion of the universe and the fact that speed of galaxies increases with their distances implies that in the past they were closer to each other with less speed. They all started from one point.
Might I make a proposal? As the hour is drawing late, we have a reception after this. Could those of you who want to ask questions get together with Professor Mobasher at the reception? Or should we continue the questions now?
You have had enough of me.